So, good afternoon, one and all. Commutative algebra, that is commutative rings. Commutative rings we are discussing today. In the commutative rings, elementary concepts on the subrings and homomorphism, construction and certain rings, regular rings and Boolean rings. All these details we have learned in this unit. Today, so we element what is elementary concepts in the commutative algebra. Elementary concepts we are discussing here. So in this section, we could recall a certain important elementary concepts in the theory of rings. So the learned these your previous year's algebra or any courses. These are the say completeness of the for our reference here. But is what definition we are taking here? One definition here: a system r comma plus comma dot comma 0. So this is the real numbers, this is addition, this is the multiplication. Dot is in the 0 is said to be a ring of R is a non-empty set. Non-empty set means any elements is there in the set is non-empty set. The plus and addition and plus and multiplication, addition and multiplication are binary operations. R and 0 is distinguished element in not satisfying the following condition here. So therefore, so you see here in this condition we are taking here. So first condition is R comma plus comma 0 is an abelian group. Why abelian group? So why it is a abelian group means why is a abelian group? Addition and 0 is an abelian. Why? Because 0 is the identity. 0 is the identity, that one is a abelian group. You know that R comma dot is a semi-group. R comma dot is a semi-group. Is half of a group. That means A dot of B plus C, that is equal to A dot B into A dot C. Associative law I'm doing here, A dot C and B dot C. So for all A, B, C belongs to R. So in this ring R, so in this ring R comma plus comma dot comma 0, we are taking their operations. Plus and dot, that is addition and multiplication we are addition and multiplication we are taking here. Just a minute. In addition and multiplication we are taking here. Respectively, and the element 0 is called as 0 element or additive identity we are taking here. So for any AB belongs to R, we are taking here. For any AB we write minus A. Inverse A in the group R plus 0 and write A minus B. And A minus B, what we are writing? A minus B for A plus minus B. We are writing this is A minus B. This is minus, plus into minus, minus. By this time, so we must, knowing the several examples of the rings, not necessarily provide. Instead of saying that R comma plus comma dot comma 0 we are taking here is a ring, simply say that a ring there is no ambiguity of the operation plus and dot in R we are taking here. So A comma B belongs to R. We write R A B for A dot B. You should the following rings the respective usual addition multiplication. So we can take Z is equal to test of the integers, Q is equal to the set of rational numbers, R is the set of real numbers, C the set of complex numbers, P of X equal to the power set of X here. The set of n to n matrices is a ring where n is a positive integer we are taking here. So here, let R be a ring and A comma B comma C belongs to R, then A0 is equal to 0 is 0 here. A minus B minus of AB is equal to minus of AB. We can write minus B and minus A, we have to write minus A comma B, we have to write here in this condition here. Then A into B minus C is equal to AB minus AC. A minus B into C is equal to AC minus BC. So this is the fundamental rights and multiplication what we are doing here. Let R comma plus comma dot comma 0 be a ring. Then R is said to be a commutative ring. The operation dot is commutative. That is AB is equal to B. For all AB belongs to R. So R is said to be with identity. There is an element I belongs to R such that AI is equal to A. That is equal to IA for all. For all A belongs to R. We are writing here. So AI is equal to I is identity element to the identity element. That's why we are taking that condition here. So one definition we are taking here. One definition. So let R be a commutative ring with identity. A belongs to R. So A is said to be a unit if it is invertible with respect to multiplication. So it is invertible with respect to multiplication. Therefore, AB belongs to R. A comma B, AB belongs to R. That is AB is equal to. A is said to be zero divisor. Therefore, 0 not equal to B belongs to R. That is AB is equal to 0. Therefore, A is said to be an idempotent. A is equal to A. So A double dash is equal to some positive integer. Some positive integer we are taking here. N. But in the above, A power N is defined as inductively A power N into A power N minus 1, A power N minus 1 into A power N minus 1 into A, N greater than 1. It can be easily verified that the set of units a ring or From's group of under multiplication. So therefore, if A is a unit in R, so therefore, then there is a unit B belongs to R. We are writing AB is equal to 1. So this B will be denoted by A inverse. That is I and only element which both unit are both a unit and idempotent. So the zero element is only the which both the nipotent and the idempotent. So therefore, there is non-trivial and zero divisor. That non-zero nipotent is always zero divisor. We are writing here that is A is equal to 0. Then A power N minus 1, A power N minus 1 not equal to 0. A into A power N minus 1 is 0. And also note that R is not a divisor, then R is always zero divisor. Then definition. Let R be a non-trivial commutative ring with identity. R is said to be another definition, non-trivial. I am taking the definition. Let R be a non-trivial commutative ring with identity. So therefore, R is said to be an integral domain. R is said to be an integral domain already in the algebra. So if G0 is the only divisor, so therefore AB belongs to R, but A not equal to 0. Why not? A is not equal to 0. So therefore A not equal to 0 and B not equal to 0. And if that is AB not equal to 0, then only AB belongs to R. So R is said to be a field every non-zero element of R, this unit. Then you must already knowing that the finite general integral domain is a field. So that is an integral domain. The ring of integers of integral domain, which is not a field. So therefore, one example we have to take here. For this problem. Let n be any positive integer and Zn the ring integers modulo n. Recall that Zn is the 0, 1, 2, n, 0, 1, 2, 3, 4, 5, 6, n minus. Together with the addition and the multiplication module for module n, for any AB belongs to Zn, A plus B and A comma B, A plus B and A comma B are defined to the reminders. We get that when its usual sum and product respectively, if A and B is derived by n, try to prove the following condition here. So what is the try to prove the same product and respectively is the same directed by to what is the proof? You have to prove that integer 1, 0, 0 less than A less than n. And if A and n is a relatively prime, Z is a field integral domain. Every element of Z is either unit or zero divisor. Zn even only every prime dividing 0. Then also n also divides A. We have to write here. Let x be any set of p of x and power set of x is defined. E of x. Just wait. So we are taking here then E of x is computed with identity. So therefore, units, Napoleons, and zero divisors are identity nodes in the rings. Next, we are discuss subrings and homomorphisms. And homomorphism. In subsystems and more and morphisms of algebraic systems are great importance. In this section, we will recalling the concepts of subring of ring and homomorphism. One definition we will take here. One definition we will take here. Let R be a commutative ring. Let R be a commutative ring with identity. A subset S is said to be S of R is said to be subring of R. So therefore, we are writing A comma B belongs to S. That is A minus B belongs to S. A comma B belongs to S. In multiplication, A B belongs to S. It is identity element 1 belongs to S. So in this case, in essence of a subset S of R subring of R, if and only S is ring with identity, S is ring with identity with respect to the operations of original ring R. It's very easy to prove that the intersection of any class of subrings of a ring or again a subring of a ring, therefore, given a subset of X of R, you can talk about the smallest subring of R containing, which is precisely intersection of all subrings, that is subring is given by X, the summation of I is equal to 1 to N, A1, I1, AI2, AI3, and so on. You can write AN1. Aij belongs to S, that is R. A minus Aij belongs to Sn, that is Ni greater than 0, N greater than 0, we are writing here. Here Ni is equal to this convention to A1, AI1, AI2, and An is a multiplicative identity we are taking here. So what is the multiplicative identity and addition identity we are taking here? But another one definition for this one, let R and S be commutative rings. Commutative rings with identities. And mapping f of R to S is said to be a homomorphism. The following are satisfied for all AB belongs to R. So you have to satisfied for all AB belongs to R. We are taking it. So AB belongs to R. We are taking here. F of A plus B, we are writing here. F of A plus F of B. F of A dot B is equal to F of A into F of B. And F of 1 is equal to 1. We are taking it here as well. See, another one theorem we have to let f of R to S be a homomorphism. Of rings. So then f of A is subring of S, any subring of A. Then R and F inverse of B is also subring of R, and subring of B of S also we have taken here. But even though we have to check this one, this is the recall that injective and subjective bijective homomorphism is called as a monomorphism, that is ectomorphism, isomorphism respectively. Homomorphism meaning of R into self is called as endomorphism. Bijective endomorphism is called as automorphism. So therefore, S is isomorphic, which is denoted by R equivalents to S we are writing here. Then construction of creation rings. Construction of certain rings. We will be learning in this section some method to construct new rings for the given. The first this direction to the product of rings. So first one theorem we have to learn here. R1, R2, and so on, Rn. Be a rings consider the Cartesian products. R is equal to R1, R2, and so on. Rn we are taking here. For any A1, A2, and so on, A1, A2, An taking here, and B, we have taken here B1, B2, and so on. Bn belongs to R. So therefore, A plus B, I am multiplying A1 plus B1, A2 plus B2, and A3 plus B3, and so on, An plus B. And we're adding here. Then A dot B is equal to A1, B1, A2, B2, and so on, An, Bn we are writing. Then R is a ring with respect to the above operations. 0, 0, the 0 element, 1, 1, 1, operation 0 element and identity element. So therefore, the direct of R is called the direct product of, the R is called the direct product of R1, R2, and R1. So therefore, we have to prove this one, this condition. How to prove here? The above condition can be extended here. A more general constant. If I belongs to I is a set of rings, and if R is 40, R is the Cartesian product. So R is the Cartesian product we are taking. I belongs to I we are taking here. Then R can be made into a ring by the defining operations. By the defining operations we are taking here plus and into. Come addition and multiplication. Addition and multiplication we are taking here. So therefore we have to write here f plus g into y is f of I into g of I. F of g into y, f of I into g of I for all I belongs to also we are taking. So therefore we are taking here if Ri is equal to yes for all I belongs to y. So then the above R will be defined as S dash. R will be defined as S dash, in particular n greater than 0. We write S power n the product S into and so on is. So n copies of S we have to write. This is the one. So therefore A plus B into B, the value is correct. Then we have to go on another theorem. Let R be a commutative ring with identity. Let R be a commutative ring with identity. And R of X we are taking here. Denote the set of polynomials or in the indeterminate. R of X equal to also we are taking here. R of X also we are taking here. A1, let's say 1x, A2x, A3x, and so on. A and X and n greater than 0. A belongs to R. So then f of Rx is commutative in identity under usual addition and multiplication of polynomials. So then proof, we are taking the proof here. Let to you an exercise that recall the addition and multiplication percent dot the polynomials are we are writing here a1, a1x, a2x, a3x, and so on, anx, and b naught, b1x1, b2x2, and so on, bn xn, x power n, m and m, b power x power n, m. So this is A naught, you have to take A naught. A naught we have to take here. Question here. So B and Xn we are taking here. So therefore, B and Xn. So what we have to write here, this one, A naught plus B naught, B1 plus B2x plus B1, A2, B1 plus B2. A naught, B1, A1, A1, this is A1. A1 plus B2, A2 plus B2x square, A3 plus B3 x cube, and so on. So what we are taking x square x cube is what we are taking a common here, and so on. An plus Bn whole power x power n. So and we are writing A0, A1x, and so on plus An xn x power n. In my addition, multiplication is B0, B0, B1x, B1, and so on, Bn. X power n, we are x equal to C0, C1x plus Cn plus m, n plus m. So therefore, the C power k is equal to summation of I is equal to J is equal to K, AI Bj. So therefore, A0 Bk, A1 Bk minus 1, A2 Bk minus 2, and so on AK Bn we are writing here. Note that there's either above definitions we have A is equal to 0, I greater than n, Bj is equal to 0, J greater than n. Note that R can be identified as subring of R of x. It can be verified R of x integral domain. R is an integral domain, R of x is an R. So even R is a field, we call the following important result in the theory of polynomials. So then the division of algorithm. The division of algorithm. The division of algorithm. So let R be a commutative ring with identity. Let R be a commutative ring with identity. Let R be a commutative ring with identity. And R of X. The ring of polynomials over R. Let X into G of X belongs to R of X we are taken here such that G of X not equal to 0. If of X, G of X belongs to R of X, G of X not equal to 0. And the leading coefficient here, the leading coefficient is to power is to power X and Gx is a unity norm. So therefore, Q of X and R of X belongs to these two values are Q of X and R of Q of X and R of X belongs to R of X such that we have to write here of X equal Q of X and G of X with R of X. R of X is equal to 0. Then degree of R of X, degree of G of X. So degree of r of x, degree g of x we are taking here. So therefore, we are taking here r of x is equal to 0. So r of x is equal to 0, there is a degree of r of x and degree of g of x. As a consequence of the division of algorithm, we can derive that the element of r is the root of polynomial. If f of x is equal to 0, deriving that is x minus a. F of x is also known to derive the remainder theorem. F of x is x, we can get that f of a is also a remainder. Is x minus a, f of a is the remainder. So that is what we are taking here in this condition also. One question. Let R be a commutative ring with identity and R of x be the set of all the formal power series sum of a to 0 is equal to 0 n. Let R be a commutative ring with identity. R of x be the set of all formal power series summation of a is equal to a n x and r power x. Therefore, r power x we are writing a summation of a n is equal to 0 to a n x and a n belongs to r. So we are let us consider we are taking a let us define here. Let us define here summation of n is equal to 0 to infinity a n x n summation of n is equal to 0 to infinity b n x n. So a n is equal to b n for all n. So a is equal to summation of n is equal to 0 to infinity a n x n we are taking here. So therefore b is equal to summation of n is equal to 0 to infinity b n x n. So summation of a is equal n is equal to 0 a n x n b n x n both are belongs to under r of x. So these both are belongs to under r of x. So therefore I am adding here a plus b summation of n is equal to 0 to infinity a n plus b n x for n. A dot b is equal to summation of n is equal to 0 to infinity c n x n. So a plus n is equal to, they are taking c. So therefore c n is equal to what we are writing a z a n plus b n. Sorry, a0 plus b n, a0 b minus 1 and so on a and b is 0. So these are values of the array. Prove that R of x cumulative with identity R is a subring of Rx. The next these methods are identify certain subrings of the ring of the real numbers and the complex numbers we are doing here. So example, some examples we are taking here. Some examples we are taking here. Just a wait. first example, let Z of I be the set of all complex numbers whose real and imaginary parts of the integers. So the Jedi is all complex numbers whose real and imaginary parts of the imaginary is what I Jedi is equal to A plus B, that is A comma B belongs to Z. So A plus B, what we are taking here, I know A, so A plus B belongs to. So then it can be easily verified that Jedi is a subring of the ring, but complex number, that is we have to, that is a complex number. There is a complex number what we have to see here. There is a complex number that is we have to see here. Subrings of the ring C. In this fact, Jedi is the smallest subring of the ring. So we have to write Z union of I. We are right here, and also Jedi we have to write here as an integral domain, which is not integral domain, but it is not a field we have taken here. Note that Z is a subring of Jedi. Notice that Z is a note that Z is a subring of Jedi we are writing here. Then second condition, what we are taking here, let Qi x plus yi by x and y are rational numbers. X plus y, x and y are rational numbers we are taking here. So the Qi is the smallest subring of C. So therefore, continue Q union of I, where Q is the set of rational numbers. So therefore, Q is the set of rational numbers. So therefore, Q is the field. So therefore, we are taking Qi is the field for the above condition is satisfying here. Then third one, let P is a prime number. Let P by any prime number. Let P by any prime number, then it will know root P, that is a positive square root of P, that is an irrational number we are taking here. So therefore, what is the exact Z root of P that we are taking here? Condition A plus B root P, that is A comma B belongs to Z, we are writing A plus B root P. So then Z of P, I am writing it is a ring of under the usual addition multiplication of real numbers. This is a smallest subring of R and the real computing Z union of root P. So Z of P we are taking that these one we are taking the ring of R real number union is an integral domain. Integral domain, but this is not a field we are taking. It is not a field, that one. That is not a field. Then regular rings and Boolean rings. Regular rings. Regular rings and Boolean rings. So in this section, two special types of rings will be introduced in the Boolean rings also. The first type, ring of sufficiently. It's sufficiently we are taking here. Idempotenants, and while the second type is the every element in idempotent, the formally defined as following. So a ring we are taking here, R comma plus comma dot comma 0 with identity and said to be a Boolean ring if every element or is idempotent. So therefore, that is A square is equal to 0 for all A belongs to R. Idempotent we are taking here. So idempotent, the power set of P of X, if any set is Boolean ring, and the operations defined here. So therefore, the Boolean ring is must already knowing that every Boolean ring is necessarily commutative. So therefore, we have to clause rings which is generalized of the Boolean rings. One definition we have to learn here. Let P be a prime number that is R comma plus comma dot comma 0 be a ring with identity. The R is said to be a P ring, that is A square is equal to A, then PA is equal to A for all A belongs to R, for all A belongs to R. So when we say about that is PA between A plus and so on plus A, we are taking this is P times we are taking here. So if A is an elemental Boolean ring, A plus A is equal to A plus A whole square. That is we are writing A square plus A square plus A square plus in Boolean in place A plus A means 2A whole square. This way to write A plus A plus A plus A. This is A plus A is equal to 0. This is in a Boolean ring. In only Boolean ring, that's why we have to write this one. A plus A 2A whole square. But A plus A whole square is A square plus A square plus A square plus 4 times we have A plus A plus A in a Boolean ring. We have to write this property, this one. Another theorem, let P be a prime number and ZP, then the ring of integers of modules, then the ring of integers of modules, let X be any non-empty set, ZP whole power X, let this for all in mapping of X in ZP. So therefore, P ring with respect to the operations, f of plus g into X is equal to, I already told f of X is the g of X, f of g into X, f of X into g of X for all f of into G belongs to Z belongs to P and X belongs to X. We have to write this in condition. This we have to prove here. Note that we know that plus and addition. At the right hand side, the above definition and the modulus of P, multiplication module of P respectively, you can easily clarify that ZP is P ring using that can prove that ZPX is also a P ring. ZP also is a P ring. We have to take that one. Another theorem also we have to do it. Just a minute. Every P ring is commutative for any prime number P. So therefore, proof what we have to take in here proof. Let P be a prime number. Let P be a prime number of, and P is a P or a P ring or a P ring. A power P is equal to 8, that is we are writing P is equal to 0. So all A belongs to R. For any B belongs to R, consider. For any B belongs to R, consider here A plus B is equal to A plus B. So in place of B, I'm writing A plus A whole power P is equal to A power P minus 1 into B. a to p power minus 2b square and so on plus a into bp power minus 1 plus b power p, where a dash of b dash is the sum of products of the elements can be the terms of which a appears, three times of b appears, three times of appear. So therefore a square b is equal to a square b plus ab a. So the b a square. Suppose a power p that equivalents to a. So b power p that equivalents to b we are writing here. A power p means a, b power p, b power p means b. From the equation 1 we are getting here. So a power p minus 1 into b plus a power p minus 2 into b. So therefore plus ab into e power minus 1 is equal to 0. So that 2 AB belongs for, we can replace the term 2B, 3B, 4B, and so on. P minus 1 of B we are taking here. So there are following is the system of equation. To find the system of equation here, the system of equation, the first of which is merely the equation we can write here. X1 plus X2 plus and so on plus Xn minus 1. Xp minus 1 is equal to 0. 2x1 plus 2 square x2 and so on 2p minus 1 x2 minus 1 is equal to 0. 3x1 2x square 2 p power minus 2 power minus 1 is equal to 0 and so on p power minus 1 x1 p minus 1 x square plus p minus 1 p power minus 1 x power p minus 1 is equal to 0. Just p power minus 1 and p minus 1 whole square, p power minus 1 into p power minus 1. So under 1, 2, 3, 4, as usually writing unto p power minus 1 we are taking here. Where x dash we are taking here. Where x dash a into p power minus 1 b dash 1 less than or equal to y less than or equal to p power minus 1. Let m be the the determinant whose I and jth determinant ith jth entry, that is we are at I into jij. So m1, m2 and so on. mp minus 1 be the cofactors of the first column of m. It multiplies the system of equation m1, m2, m3 and so on, mp minus 1 respectively. We add that here mx1 is equal to 0. mx1 is equal to 0. So now m is known to be proud of positive integers less than p. Therefore, m is relatively prime to p, so that the integers s comma t, ms plus tp plus 1. So ms plus tp means I'm multiplying m into s and t into p. So therefore, x1 is equal to m into s plus t into p. x1 smx plus tp x1 is equal to 0. We are writing it. So thus we are writing AP inverse B. AP inverse P minus 2 BA. ABA P minus 2 plus BA P minus 1 is equal to 0. We are writing here. So by it can easily also we can take here. Correct. So AB is equal to BA. So there is R is a commutative. Therefore, R is a commutative. So then we can next introduce another class of subring follows also. The class contains the class of P rings or any time P. Then definition. Another definition also is have to take here. The commutative ring R, its identity is said to be a regular ring if for each A belongs to R, there is an element of B belongs to R also. So that is why A square B is equal to. So in the obviously P ring is regular ring of premises for P. P ring is commutative ring identity A power P minus 2 is equal to A. Following element, the converse is not true. The regular rings is P rings, they consider the following conditions. So an example you have to take here. Let X be in set and the real numbers that affect the usual addition and multiplication numbers we are taking here. F comma G belongs to R here. So already we know that f of plus G into X is equal to f of X plus G of X. F of X plus G of X we are taking here in multiplication of X into G of X for all X belongs to X. ఇద్దరి ఇస్తే కలిపే చేసిస్తా అంటే ఓకే f of X, G of X for X belongs to X. So therefore, we are taking here the commutative ring with identity. There is no prime number P such that f of X belongs to X. Example, we are taking here G of X. G of X we are taking here. Here we are G of X taking here. G of X is equal to 0. If f of X is equal to 0, 1 by f of X is not equal to 0. Therefore, f of G is equal to f is we are taking. So this is the note that it is a regular ring of any element A, there is an element B, such that A is equal to A square. But AB whole square is equal to also AB. But therefore, in each element we are taking here, we can associate idempotent, C in the way duplicating A. Also note the subring a regular ring is made to regular ring. The ring of the real numbers regular ring in fact, it is a regular ring. So therefore, it's a easy. This is the first one. Then we'll go such ideals. What is the meaning of ideals? Ideals. What is the meaning of ideals? In the ideals and quotient operation ideals, prime prime ideals and null radical sum. So ideals and quotient ideal rings. So we call the important concept of ideals and quotient rings from this one. Also, the summary of the importance of the results of this one in the we have studied in the algebra also. This one from the onwards throughout that we always mean a commutative ring with identity which I not equal to 0. Commutative ring with a commutative ring I not equal to 0. So what is the definition of ideal? Ideal definition, we have to follow ideal definition here. Synonymity set of a ring or said to be an ideal or so therefore A comma B belongs to Y, but A plus B belongs to Y. And A belongs to Y and R belongs to Y, that is RA belongs to Y. So AB belongs to Y and RA belongs to Y. So intersection of a class ideals of a ring, or is again ideal R for x is subset of R1 x1, R2 x2. So therefore you have taken here x R1 x1, R2 x2, and so on Rn xn. So R1 belongs to x and Rn belongs to R, n greater than G. Is an ideal, in fact, the smallest ideal of R containing x and is called the ideal generator set. X is, you can easily verify that Rx R belongs to R. So here x, that is Rx, we are taking here Rx by R belongs to R. You can Rx R belongs to R. Taken here only. So then not your take note that Rx is called the principal ideals generated by x and that Ro is R. Or you must also note that it's the smallest ideal why R is the group of R. Sometimes the denoted is simply zero. Any ideal different from R is called as proper ideal of R. We are writing this one. Then one question we have to see here. If C is a chain of ideals, C is a non-stop ideals for any I comma j belongs to G. I comma j belongs to C. Whether I subset of equal to J subset of equal to I, prove that union of I belongs to I is an ideal of R, is an ideal of R. You have to prove it. But we have what we have to taken here. In the following, you will be seeing that the details, ideas are preciously the kernels of the kernel of homomorphism can left into some ring of S or else subrings or R. That is f of R to S. F of R is the homomorphism. The kernel of F is defined by what is the kernel of F? What they are writing here. Kernel of F here. A belongs to R by f of A equal to 0. Kernel A belongs to R, so therefore f of A belongs to 0. You can easily check the kernel F is an ideal of R. Conversely, suppose if is an ideal of a ring, F is an ideal of a ring, then the set of all cosets I in J forms in which all denoted by R by I. So let R by I we are taking here R by I. A plus I by A belongs to R. So now A comma B belongs to R. So A plus I is equal to B plus I. So if and only that is A minus B belongs to Y. So AB belongs to R, A plus I, B plus I. This is a plus one I'm taking here, that is A plus B. I is common taking here, that is A plus B into plus I. So A plus I in multiplication, this is multiplication, B plus I, that is we have to write AB plus I. This is addition, this is multiplication we are taking here. Then these two are well defined binary operation by R by with respect to R by 0 plus I is the additive identity, 1 plus I is the multiplicative identity. R is called as the quotient ring of R. Then the additive inverse of the A plus I, that is minus A plus A also. That is the additive inverse to A plus I. Maybe R by I is we can write minus R plus for minus A plus I we have to write here. So all any A belongs to R, A plus is unit of, you can write A plus B is equal to A minus B minus 1. A B minus 1 belongs to I. A B minus 1 belongs to I. So therefore A is unit of R. So A plus I also uses in R by I in unit of R in real numbers. So define here in R belongs to R by N. Pi of A is equal to A plus I for all A belongs to R. So here, then pi is a homomorphism is called as a natural homomorphism into R by I. So note that kernel of phi is respectively I. So thus the ideals of R, precisely kernels homomorphism of R. The following theorems are known to you. Recall the sections of 7.6 course 1 algebra earlier of this course one also algebra we have to learn in the first year. So therefore, this is also ready for reference, but you can use it also in fundamental theorem of homomorphism. Fundamental theorem of homomorphism. Let R and S be subrings. Let R and S be subrings. F R to stand states of homomorphism. F of R subring of S. Kernel F is an ideal, and R is the quotient ring. R by kernel F of R under the homomorphism of A plus kernel of F stands to F of A via PVA. In particular, it is an epomorphism that is different idea. R by kernel F is equivalent to this. Let F be an ideal ring. So another one, let F be an ideal ring, that is R and R by I. The quotient of R by I, any ideal J of containing Z, J by I, A plus I by A belongs to J. J since J by a bijection of the set of all ideals are containing to J into set of all ideals of R by I we are using here in J by A plus I and J J on Mulakalam in the elements of in J, all the elements is there or is there. Then operation on ideals. Operation on ideals. So let R be a ring. So therefore, let us write R of X, R be a ring and write IR. We denote the set of So see here, and we are continuation of this problem. Written here. So therefore, I intersection J we are taking here A belongs to R. That is A belongs to A belongs to A and A belongs to J. So both are I elements in the an element in the I, an element in the J. I plus J we are multiplying A plus B. That is A belongs to I and B belongs to J. So this is also this is B belongs to J. Then we are adding I into J, A1, B1, A2, B2, and AN, A belongs to I. B1. You can easily verify that I intersection J, I plus J, and Ij are details of R. Also, these operations are commutative and associative. The sense of any ideals Ijk we get here, I intersection J. I intersection J is equal to J intersection I. So I intersection J intersection K is equal to I intersection J and intersection K we are writing here. So therefore I intersection I plus J we are writing here. I plus J is equal to J plus I. So additive property we are in associative property we are write I plus J plus K is equal to I plus J plus K we are writing here. So Ij is equal to Ji we are writing here. So I into in multiplication process Ij into K. So this is the one of the intersection and addition idempotent. Intersection of I is equal to I plus I is equal to I. Why? While 2 greater than equal to Y. Any ideal of any non-negative integer you can define indexically as follows. That is I power 0 is equal to R. I power n is equal to I power n minus 1 for any n greater than, for any n greater than 0, the condition may be satisfied here. And another one theorem we have to do here. Another one theorem we have to check here. Yesterday. Let Ijk be an ideals of a ring or such that I intersection K such that I intersection J plus K, I intersection J plus K. So what we are taking here, I intersection J plus K, I intersection J plus K. So therefore, what we have been here. So what we I intersection j plus k, I intersection j, what I intersection j plus k, I intersection j, and I j plus k, so we have intersection I. After that I intersection j, we are what we are doing here. Then I intersection j, then we are adding k. So therefore, I intersection j, since we are taking here j intersection j plus k, I I intersection j, subset of I intersection j plus k we are writing here. So therefore, k intersection j by hypothesis, k subset of j plus k we have k subset of is equal to I intersection j plus k we are writing here. Intersection of k intersection of I intersection of j plus k. So combining the above to get here I intersection j plus k intersection I intersection j plus k. So we prove that I intersection j plus k, subset of I intersection j plus k. We're taking here A belongs to I intersection j plus k. So that is the condition. In additive property, we are doing here A belongs to A is equal to B plus C, B plus C belongs to K. What that we have doing here. Then C belongs to Y, then B is equal to A minus C belongs to Y. We are taking here B belongs to I intersection J. We are taking here A is equal to B plus C belongs to I intersection J. We are taking here. So therefore, I intersection J plus K, subset of I intersection J plus K. So this is the theorem has been proved here. And also the ideals are justifying the properties I intersection J is equal to 0. I plus J are special intersective for any displays r is equal to r by a by r by j. Then the generator state this of the following statement here. So therefore what we have to do here, then let I1, I2, I3, I4, I4, In ideals bearing such that every I1, I1 or I0 equal to j, intersection of I is equal to n, I is then r by I is equal to r by I1 and r by I2 and r by I3 and r by In. So how we can think it is defined R to R by A1, R by A2, and R by AN. So that we have to take f of A is equal to A plus I1, A plus I2, A plus I3, and so on, A plus IN. So what we are taking here by the integral part, that is the addition part, A plus I1 taking here, we can easily check the homomorphism of rings. We can easily check the homomorphism of rings. F is equal to I1 intersection, I2 intersection, and so on. In is equal to I. So it was proved that F is onto. Onto means Anvegam onto by the fundamental theorem of homomorphism, that is R by I is equivalent to R by I1, then R by I2, then R by I3, and so on R by N. So now we shall prove that F is onto for any x belongs to R by I1, R by I2, and R by IN. So A belongs to R, therefore f of A is equal to x. So that means we have to write here A1 plus I1, A2 plus I2, and so on, AN plus IN. So we are taking the existing A belongs to R such that we are taking here f of A is equal to A plus I1, A plus I2, and A plus IN we are taking here. So therefore A1 plus I1, A2 plus I2 and so on, AN plus I. So what we are taking here, these conditions, so A minus, that is we are writing here, A minus AI belongs to I for all 1 greater than or I less than or n. So we have to prove the following conditions, this one. So f of A, so therefore f of A is equal to f of A is equal to what we are taking here, A plus I1, A plus I2, and so on, A plus IN. So therefore, anyone A1, A2, A3, AN belongs to R. There exists A belongs to R such that A minus I belongs to I. For all I1 less than or equal to I less than or equal to N. We shall prove that induction n is equal to 1. This is a trivial that n is equal to A1, A2 belongs to 2. I1 plus I2, I1 plus I2 belongs to R. We can choose B1 belongs to I, B2 belongs to I2. So therefore B1 belongs to I, B2 belongs to I2. B1. So that when B1, B2 belongs to I1 and I2. So therefore B1 plus B2 is equal to 1, the condition. So therefore now A is equal to A1 B1, A1 B1 and A1 B2, A2 B1. So therefore A1 is equal to A1 dot A1 B1 A2 B2, A2 is equal to A2 B1 A2 B2. So there is a condition A minus A1, A1, A minus A1, A1 B2 plus A2 B1 minus A1 B1 minus A2 B2. We are right, taking the combination here, B1 belongs to Y. So A minus A2 is A1 minus A2 B2 belongs to I2. This is the condition, this one. Any doubts, ask me. Tomorrow we'll continue this.